this video, I host a Q&A for my students, which is focused on solving the transformation style questions. Enjoy. So basically for this class, we'll have a look at transformations in a bit more formal detail. We'll go through it in... there's an approach that I use that is less commonly taught, at least as far as I'm aware of, in schools. Backstory being that I personally used to struggle a lot with transformations when I was doing it in school. And since tutoring, I figured, well, okay, what's a different way we could do this? And there was one way that was actually presented in the textbook, but for whatever reason wasn't really taught in the schools, and so, well, in my school anyway. And so what I'll do is I'll share that method in hopes that it makes your transformation style questions a bit on the easier side. So, okay, let me get the notes up for that. So you guys are at some level of understanding of transformations, at least if not globally. We talk more so in terms of the individual functions themselves. At this point, a lot of you would have seen linear, quadratics, that sort of thing, and how each of the terms effectively impact the shape of a graph. Those are called transformations, and what you'll find is that the way that they are presented in functions is often quite consistent with how they apply to all types of functions, whether it be quadratics, cubics, hyperbolas, and other functions that I could name. To make it more applicable across the board, to understand this in a bit of a deeper level, we think about things not necessarily in terms of functions, but in terms of the individual points along a curve, and just seeing how they are transformed from state to state. So in 3 steps, you can apply any transformation by starting with figuring out what that transformation even is, whether it's a translation, dilation, or reflection. Rearranging those terms to get x and y on its own. You'll see what I mean by that in a moment. And then substituting that new rearranged x and y into your function. So we'll have a look at each individual type of transformation, and we'll see how that process can be applied to transform a function. So first one up, dilations. Dilations are all about stretching your function. The idea here being that you stretch in a particular direction, either from the y or from the x. You might also see wordings like along the y or along the x. When you see this kind of wording, these two things mean the same thing. If you're stretching along the y-axis, it's the same thing as if you're stretching away from the x-axis. So if I draw a quick visual on the handwritten section, we have an axis, we have some point. Here's my y, here's my x. If I stretch along the y, that's going in this direction, right? It's going along, parallel to the y-axis. Alternatively, another way of thinking about that is that it's getting further away from the x. Those two terms mean the same thing, despite them talking about different axes. The keywords that precede it will be the thing that you have to care about a lot as well. From experience, the book will typically use from an axis. That'll be both Cambridge and Jacaranda. But I've seen some exam questions from other companies that will put like along an axis in there. Suffice to say, both ways of wording something are the same there. Now, how does this actually work? Dilations, being that they stretch, are effectively a multiplication of whatever variable you have. So if we're going along the y from the x, whatever it is, in the y direction, that is a multiplication of the y variable. So you're starting out at some original point, x comma y, and you're moving to some new point, x comma a times y. So again, if I go back to that drawing, if this was x comma y, then this new point up here shares the same x value, but has been multiplied by whatever a is on the y. Okay, how this works, we use x dash and y dash to represent the new coordinates. So x dash is going to remain as x hasn't changed, y dash is going to get ay. From there, rearrange to get x and y back on their own. The reason why we're doing that is because we want to figure out what our new function, y equals f of x, is going to be, where f of x could be any function. quadratic, hyperbola, truncus, whatever. When you get x and y on their own, you'll see what you have to replace them with. X is going to remain as x. The new y is going to be y over a. So you have whatever the function is, y over a equals f of x, and then because we're dealing with functions, we just replace, we get y back on its own, which means multiplying both sides by a. If we have a look at an example, so one thing you might want to do is apply a dilation of factor 2 from the x of this function, this square root function. So one way of doing that, again, if it's a dilation factor of 2 from the x, that is a multiplication of 2 on that y variable. It's going away from the x. That's going to give you x dash and y dash. Rearrange those for x and y, and then sub those into the function. X doesn't change, y does, and then you rearrange to get y on its own. This might seem a bit excessive for the amount of effort you have to put into just solving one transformation, and it is for one transformation though. When you start having to do multiple in a specific order, that's when this starts to become a bit more powerful. So what I've done in each stage is just sort of show you the shortcut for what each transformation looks like. A multiplication of a on the entire function is a dilation along the y or from the x. So you can skip all of this and just go straight to multiplying the 2 out the front. So if you have these simpler examples, yeah, by all means go ahead and just use the shortcut. But we will have a look at this process because it helps with the more complicated scenarios. If anyone has any questions as to how that works, please put that in the chat. Otherwise, we'll keep doing these at a bit of a faster pace once I take a sip. Okay. Also dilations, this time in a different direction, along the x or from the y. Same idea, but now we're applying it to the x. The exact same steps, but this time x is getting the a value. So when you sub that into your function, you'll notice that no further rearrangement needs to be done. We only care to get y on its own, and y is already on its own. So if we just compare the differences here, this dilation factor of a ends up appearing as a division, whereas this one ends up appearing as a multiplication. Bit weird. So if you've seen anything like this before, hopefully this 3-step process is sort of shining a bit of light as to why they might appear a little bit different. The main reason being we want to get y on its own for functions. That's why it flips. Whereas for x, it's remaining as a division. Same idea here. Dilation factor of 2, this time from the y. X is going to get the multiplication. Rearrange, substitute. And again, you could just sub in the divide by 2. It's a simple one. But we're just learning the process. Okay, reflections. So in all cases, for all functions, reflections appear as a negative sign on your function. They could be on the x value or on the y value. If you're reflecting in the y-axis, your negative sign goes on the x. So what that essentially means is, if I go to the handwritten section, I have some point, wherever it may be. When I'm saying I'm reflecting in the y-axis, I mean I have a y-axis, and wherever my point is, the y-axis is going to act like a mirror. And I'm going to go to the other side of that mirror, equidistant either side. And what you end up with is, this is a positive x, this is a negative x. The y values are consistent there. That's supposed to be perfectly horizontal. And so the y values are unchanged, the x has become negative. That's why when you say a reflection in the y-axis, it's actually the x that gets the negative sign. Once you know that, you go through your 3 steps, you replace every x with negative x. As an example, if you have like multiple x's, let's say, you're going to have negative on the x, and then replace all of those x's with negative x's, and then simplify from there. Okay. Reflection in the x-axis is the opposite. This time, your x-axis is the mirror, and so you're going to be flipping vertically instead of horizontally. Hence, the negative side is going to go on the y. Again, if I look at my axes, I've got some point but this time the x-axis is the mirror, and so I'm flipping downwards down to here. Vertically speaking, x values have not changed, but the y has become negative in that spot. Hence the y gets the negative. As a function, that just means you have a negative on the entire function rather than just the x values of that function. So how that looks, if you have 2x squared plus 3x, you're essentially just putting a negative sign on the entire 2x squared plus 3x and distributing through. So minor difference. This one, they were both negative. This one, only the 3x was negative. Okay, and then translations. So this is where you're just shifting the entire function in one of the cardinal directions, whether you go up, down, left, or right. Horizontal, obviously we're talking about left or right in that case. If you are shifting to the right, then you're adding to x, and if you're shifting to the left, then you're subtracting from x. Now, if you've done quadratics before, you might think that's a bit weird, because normally x minus a shifts right, and you are correct. But it's very similar to when we were looking at dilations on the x, where we had a multiplication of 2 that turned into a division. Mathematically, when you have x plus a, after you go through these 3 steps, that plus a, that shifting to the right, now appears as a minus sign when you sub it into a function. So that's one key thing to watch out for when you're doing these kinds of things. You have to forego the you have to unlearn the previously weird scenario. So x dash is x plus a, that means going to the right. When it appears in the function, it then looks like x minus a. So if you wanted to shift this side, this kind of quadratic, in this case -5 units horizontally, so 5 to the left, it just means that your x dash is x minus 5. From there, rearrange to get the x on its own, and then every x in here is going to be replaced with x plus 5. Now I've chosen to expand everything out, but fully factorizing your answer is also okay. Like for example, you could take x plus 5 out of both of these as a common factor, and just be fully factorized from there. Either is fine. And then vertical translations, that one ends up working more or less the way you expect. When you plus a, it goes up. When you minus a, it goes down. And even though it flips in this process, you'll see that because it's on the y side, we flip it back over to the, well, to the function side. So it maintains its positive being up and negative going down. So those are probably the easiest ones, the vertical translations, because you're literally just slapping whatever that vertical translation is out the front. If you're going 2 down, then you minus 2 at the front of your function, whatever that happens to be. Okay, those are all the individual transformations. Now you'll see why, or at least I hope you see, why following a point form approach will be a little bit better than just trying to sub directly into the function, at least in this case. The key thing to watch out for here is that the order in which you do your transformations matters a lot. To demonstrate this, I have 2 examples of 2 different sequences. The transformation factors are identical, but they are done in a different order. In this case, we have dilation, reflection, and some translations. In this case, we have translations, reflections, and then dilations. So let's have a look. The way it works when you have a sequence of transformations is that you're just going to repeat that first step where you identify what that transformation is repeatedly over and over again until you get through all the transformations in that order. So in this case, we have started with a dilation factor of 3 from the x. That's from example 1. From the x means that it impacts the y variable, right? It's going away from the x. When you go to apply your next transformation, a reflection of the x-axis in this case, you start where you left off. So we left off here at x, 3y. Reflection in the x means you take whatever's in the y spot, the entire thing in the y spot, and you put a negative sign on that because it's a reflection in the x. Then we had some translations. You could see those from here as well. This was 5 in the positive x, 1 in the positive y. So again, where you left off, add 5 to the x spot and add 1 to the y spot. That will give you, so this is your x dash, this is your y dash, rearrange for x and y, sub into a function if necessary. But that's a bit besides the point for this one. What I wanted to highlight here was if you now do things in a different order, you'll see at the very end, you get a different result. So in this case, we have translations first. Starting at x, y, we now have x plus 5, y plus 1. When you go ahead and do that reflection now, what you'll find is you don't just put the negative sign on the y, you put the negative sign on everything that is in that y spot. And that's why you'll find that doing things in a different order starts to matter. When you add additional terms to your transformation through translations, any dilations or reflections, pretty much any multiplications will affect both terms in there. And then last, you put your dilation factor of 3. Again, you're multiplying everything in there by 3. And so if you were to expand this out and compare the two answers, sure, the x looks the same, but this one is different. You've got negative 3y plus 1 up here, and you've got negative 3y minus 3 down here. So if you're just trying to look at the transformations that are listed and then just plug them into your function directly, you might get a bit lost on the way as to what order you should plug those terms in, and if you need to start multiplying things before subbing it in. This is where a lot of people struggle, and I've found that this 5-stage process here helps with that a lot. That is the end of at least the fundamentals of applying transformations. Does anyone want me to clarify anything in there in any more detail? Okay, so from there we can now step it up a notch. That's how you apply transformations. How do you figure out what was done instead? So instead of like figuring out, I've got this sequence and I apply it to here, can I get to here? We're now looking at two functions that are already in existence, and we want to figure out how do I get from one to the other. In the first case, you're told the transformations to apply. In the second case, you have to figure it out by looking at your functions. So again, we have a scenario where we have both dilations and translations in here. And so because of that, that's when things get a bit weird. What order do I write these terms in? What we're essentially doing here is doing the reverse of what was done in applying transformations. So here's how it works. I've got two examples in here. One that details going from a transformed state to an untransformed state, and the other which is the other way around. I have both of these examples in here not because they're different, but because they're actually the same. I want you to know that it doesn't matter what your functions look like. You can use this process no matter what to solve the order of transformations that you need. But okay, let's have a look. First step, figure out where am I starting and where am I going. Okay, in this case, we're told to find a sequence of transformations which maps f of x to g of x, starting from f, going to g. That means f of x is going to get xy in its notation, and g of x, since it's the new function, will get y dash x dash. We're going from f to g, so g being the new is going to get the y dash and x dash. Okay, next we want to figure out what all of our transformation factors are. And so what we're going to do is look at both of our functions and put everything that impacts the y on the y side, and everything that impacts the x is going to stay on that x side. Obviously nothing to be done for the second function, it is just a basic truncus. However, with this one, you've got this plus 6 and you've got this multiplication of 3. If you remember from the previous notes, this plus 6 is a vertical by 6, and this multiplication of 3 is a dilation along the y of 3, or from the x. Both of those are y transformations, and so we're going to put them to the other side by subtracting 6 and dividing 3. What's left over is purely just x stuff and, well, the framework of a truncus. So even if you're not too keen on like what's what, like what transformation factors are y and what transformation factors are x, the easiest litmus test I have for you is just move as much as you can over to the left-hand side before it starts getting weird. So what I mean by that is use addition, multiplication, subtraction, division. Don't start doing things like square rooting both sides to free the x and so on and so forth. Just keep it simple with your movements. But okay, once you've gotten all the y stuff on the y side, x stuff on the x side, this is where we directly compare each of those components to each other. If you remember, for transformations in point form, you need an x dash and a y dash that comes from some x and y. So here's the y component of our original function. Here's the y component of our new function. We compare those things directly to each other. Those are the same. Here's the x component of the first function. Here's the x component of the second function. You equate those to each other. And what we're effectively doing there is just saying, hey, here's where we started in the x, here's where we're going in the x. Here's where we started in the y, here's where we're going in the y. Now, depending on what your function looks like, you might need to do some rearranging here. In this case, x dash and y dash are already on their own, so we don't have to really do anything else. We already have our statement. This is x dash, this is y dash. Those are the transformations that we are going to list in that sequence. So this is where it gets a bit more challenging because you actually have a fair few options here when it comes to giving your answer, at least as far as writing it in a sequence of 3 bullet points, because sometimes it just wants this. Like if it just says write your x dash y dash, that's what you give. But most of the time what they care about is like 3 or so bullet points of what that transformation is in English words. So a couple ways you could do this. If you leave it like this in a factorized form, so taking all the common factors out at the front of each term, then you write your transformations in order of translation, reflection, dilation. So again, if you have it factorized, taking things out the front, it's translation, reflection, dilation. This is my personal preference for how I do it, just because this is what you do when you do functions anyway. You want to make sure there's no coefficients on your variables, so you can clearly see what the transformation factors are, at least in function land. In point form, you have a couple of options. But okay, we factorized it, translation, reflection, dilation. So from here, we've got 2 translations. We've got -6 in the y, we've got -1 on the x. X and y you can think of as independent to each other. You can do all the x stuff, then all the y, then all the x, or mix mash them together. As long as you do x in translation, reflection, dilation, and y in translation, reflection, dilation, then you'll be fine. So in this case, I've done translation of x, translation of y, and since there were no reflections in there, we're going dilation factor of 1/3 along the y, or you could say from the x on that one. You could also do the y first, as I said. So here's the 2 y things and then followed by the x. Again, as long as x is in that order and y is in that order, you can mix them as you wish. That's my preference for how we do it. But I do concede that the book will pretty much exclusively do DRT. It'll do dilation, reflection, then translation. How do you achieve that? Well, this is where you, instead of factorizing, you distribute. So instead of what I have there, if I go to the handwritten bit, we'll have 1/3 y minus 6, and I'm going to pull that factor into both of these terms, giving us y/3 minus 2. And that is the y dash that I care about. If everything is fully expanded, then you can do DRT. So under those circumstances, X is still super easy. There was nothing there. Dilation, reflection, translation of -1. So you could say -1 in X, translate. I'm just doing shorthand. You would want to use the more formal wording. And then looking at the Y stuff, you've got D. So you've got this dilation of a third. Dilate a third. You can say, yeah, sure, use from notation. From X. There's no reflections. And then finally, translation, -2 in the Y direction. TRD, TRD. Oh, sorry, DRT. My bad. DRT, DRT. So, different order depending on whether you expand or whether you factorize. Book does this. So, if you're going to pick one, then it's really up to you which way you want to go about it. As far as what would be best to go with, because there are so many possible answers to transformation stuff, what you'll find in the exam is they'll give you a question which is like, exactly like this. Figure out a sequence of transformations. And what they'll do is they'll go out the top and they'll give you either a T or a D. And that's going to force you to do one or the other. Because if you're starting with translations, then you've got to care about doing TRD in that order. Versus if they give you a dilation first, then you want to use the DRT version where you're doing your expansion. So it's worth understanding how both work. You're now seeing how both work here. Is it clear the differences there in when you use what? We'll look at another example. As I said, we have another example. It is going to be fundamentally the same thing. So again, start by figuring out where do we start, where do we go. We're starting from F, we're going to G. So F is going to get X and Y, G is going to get Y dash and X dash. From there, what's the Y transformations? They go to the other side. Everything that's X stays on the X. This is untransformed, nothing changes. This is transformed, so you subtract your 3 and you divide your 2. From there, compare the X and the Y's together. Here's the Y of the first. Here's the Y of the first. Here's the Y of the second. Those are equated. Here's the X of the first. Here's the X of the second. You compare those. One thing I didn't really super well specify is why we don't do the entire right-hand side. Rather, we just take the individual transformations. That's just more of a shortcut, really. If you just take what's inside the brackets here as the actual transformation aspect of the function, all it does is speed things up a little bit. So an equivalent way of going about this would have been literally to do x squared equals x dash minus 2 all squared. So I'll do that now on the handwritten bit. So it was x squared equals x dash minus 2 all squared. If you want to get your x dash on its own, the very first thing you're going to do is just square root both sides. And just like that, you're already back to what you would have had if you were just taking the transformations. So it's really just a time saver, just to take the transformations rather than the whole thing. But if you're not super keen on understanding which one's a transformation and which isn't, then by all means, take the entire right-hand side. It's just going to take you like 1 or 2 more steps to get there. But it's at least a good starting point for understanding how this works. Anyway, as I said, rearrange for your x dash and y dash. If you remember the previous example, we didn't have to do anything. In this case, we do. X dash and y dash are trapped inside the functions. So we're just going to rearrange a little bit. That gives us our y dash and our x dash. From there, we give our transformations in whatever order we care about, or whatever order is forced onto us by the question. In this case, it was already distributed, so if you're looking to be super like efficient with what your function looks like, you would do DRT for these. Just to make things consistent in the book, in my notes anyway, I took a common factor of 2 out the front and then did TRD instead, but either's fine. If you're doing DRT, this would be dilation factor of 2 from the x, or along the y, 3 in the positive y, 2 in the positive x as translations. You'll do it in that order. Otherwise, if you're doing TRD, just be sure to take that common factor of 2, well, I say common factor, take the factor of 2 out the front, and then do TRD instead. So translation of 3 over 2 in the positive y, 2 in the positive x, and then dilation of 2 along the... Did I do this? Oh no, I did it y first then x. So you can see there's a whole bunch of ways you could do it. As long as you do y and x individually, you're fine. Any further questions about that? A fair bit to go through. This was all of 7a through D. So I'd be shocked if there were any things left to clarify. So if no one has any like specific questions, maybe we'll just start looking at doing some of the actual questions in here. So page 266. Okay, this one purely looks at translations. So from there, this is taking a step back in difficulty significantly. What I'll do to hopefully make life a bit easier is do a few screenshots. I'll put some of the processes that we follow into the chat as screenshots, and then we'll apply those to these questions. Okay, those should both be sent. Cool. So we have this image, we have this point, and we're trying to find the image of that point after mapping a translation. The image of a thing just means where does it end up, really? If you think about like, what would be a good analogy for that? Yeah, what does it look like after it's been applied? Maybe that's one way of looking at it. So if we have the point -3, 4, you can think of that as your x and your y, just regular old xy. You're then transforming that into a certain thing. In the case of 1a, we're doing 2 units in the positive x and 3 units in the negative y. With that understanding, being that it's a translation, what do you think I'd do to my initial xy to make my x dash y dash? What should that look like? This is where we'll go interactive, I'm hoping. All right, I'll do the first one. You guys can do the second one then. Cool. So 2 in the positive x simply means you're starting with whatever your x is, and you're adding 2 to the x variable. 3 in the negative y means you're starting at whatever your y was, and you're subtracting 3 from that. So if we have the point -3, 4, that means x equals -3, y equals 4. So when we put that into our transformation, we now have -3 plus 2, oops, should not put a bracket there, and then 4 minus 3. Giving you a final point of -1, 1. Okay, hopefully I've done the math on that one right. Looks about good. Okay, I can do addition, nice. On to 1b. So again, we're just dealing purely with translations here. We're starting at the exact same spot, -3, 4. This time we're doing 2 units in the negative x and 4 units in the positive y. What's it going to look like now? X minus 2, y plus 4. Yeah, -2 on the x, plus 4 on the y. Correct. And so what does our new point then look like after you apply that? -5 and 8. Indeed. Yeah. Perfect. So fundamentally, just addition and subtraction. That's all we're really doing here, just there's a whole bunch of words around it that you have to now digest. C is the same thing. You'll recognize D and E based on the way I've done it. What do you think the point is going to look like after we go through D? Minus 7,9. Yeah, precisely. So again, addition, subtraction. Cool. Okay, what's 2 got? For each of the following, describe the translation. Okay, yeah. Slightly different take on it now. So now we're doing these things here. So we're trying to figure out what this would look like to get from this point to this point. So I'll give you guys a shot to try and do that yourself first. And if I get no responses, I'll do the first one. 5 units left, 3 up. Yes, that's what that would look like in a worded form. Could you write that or otherwise explain that in this notation here? X comma y maps to some new function. X minus 5y plus 3. Yeah, exactly. And that would be what this right-hand side would look like. You always start with your x comma y, arrow, and then, as you said, Ricardo, x minus 5, y plus 3. Cool. Same thing for both of those. In question 3, we're now taking those transformations and then applying them to a certain function. Now, these are technically on the easier side. You don't really have to do the whole swap x and y and then rearrange and sub into function. You can just directly smack them into the function where you expect them to go. For the purposes of this, it might be good to practice doing both ways. Just up to you, really. So, question 3. You have a hyperbola. It's going 2 in the positive x, 1 in the negative y. What does that function now look like? If you're going to type it, then probably use brackets to make the fractions look a bit nicer. One of x take 2 and then minus 1. Okay. 2 in the positive, yep. 1 in the negative, yep. Cool. So just to make sure everyone's super clear on what was typed there, 1 over x take 2 and then minus 1 at the end. That's your new function as that hyperbola looks. So again, in function land, x minus 2 means a shift right by 2, and then anything you have out the front is a vertical translation. It'll look very similar for 1 over x squared, part C, part D, part E. They're all the same thing. I'll leave that there unless anyone wants to put in the chat and ask me to clarify any of those. Honestly speaking, from 4 to 6, it actually ends up getting a bit easier, because if you're familiar with function notation, this literally just means everywhere that you see x, you replace with x minus 1. You don't even need to know what that even does to the function to know what that'll end up looking like, at least as a rule. It does say to sketch it, but that's a bit beyond what we're trying to do here. If you haven't seen these functions before, we'll purely just focus on the translation side, or the transformation side of things, rather than what they look like as graphs. So that's just subbing stuff in, nothing too crazy there. Dilations, reflections, same deal. All right. So in this case, you're just multiplying either by negatives for reflections, or you're multiplying the entire value. Okay. So if we do like maybe a few of these, we'll pick, yeah, why not? So again, we have some point. What would a reflection in the x-axis on this point look like? 1a. 2 comma negative 3. Almost. So reflection in the X means the X axis acts like a mirror. So this is where people get tripped up because of how the wording is. So to demonstrate this, I'll draw the axes and show you the point. So -2, -3 would be like this, basically. And so when we... Okay, did you actually mean to type? Yeah. I mean, I'll finish the explanation for this anyway, just for fun. When it's in the x-axis, then you flip vertically. And when you do that, it's the y that ends up changing. So that's why it's going to be -2, 3, rather than what you initially typed. So there's that. And then maybe just quickly, who can tell me what this part D would look like? Dilation factor of 4 from the y. -8, -3. Yeah, checks out. From the y means it impacts the x. Nice. This one is a lot. It's just, again, doing the same sort of thing we were seeing before, which was figure out your transformation, rearrange it for x and y, plug it into the thing. In this case, because they are individual transformations, you can just look at your cheat sheet, which would be like, I know I didn't really screenshot it, but there's these little cheat sheets to say, hey, look, this is how it looks like in a function, this is how it looks like in a point, so on and so forth. So you could just cheat, well, not cheat, you could use the shortcut there for those. Just so we can get into some more complicated stuff before class ends, we'll look at the combinations of transformations now. So this is where doing that sequence now starts to matter a fair bit. Just to briefly recap what's going on there, you do them in order. So dilation factor of 2 from the x means you go x, y, and then x, 2y. Then you have your reflection in the x. That means a negative sign goes on the y. That's your new x dash y dash. Rearrange for x and y, sub into function, or answer whatever the question's trying to do. Like in this case, there is no rearranging, it's just plug your x and y into there. So we'll do 1a on this one. So you have your starting point, translate 3 into positive x, then dilate by 2 from the x. Five and -2. Yeah, exactly. The rest is just different mix-mash variables of that. Part 2 is now applying that to function. So what would that now look like in a function rather than as a point? So is that just a repeat? Yeah, we'll pick one that has like, I don't know, we'll go C. Reflection in the x, then dilation factor 3 from the x. That'll be a fun one. If you want to type the root out, maybe just spell root. -3 square root x. Yeah, exactly. Nice. Question 3 and 4, just repeats of that. The function has basically no impact whatsoever on what you do. You're still following the same procedure. Same thing, same thing, same thing. No, 7's slightly harder because now you're not starting with... I say harder, but because you're doing this, well, at least I hope you're doing this procedure, it effectively just means even though it looks different, like it's already been transformed, you still handle it the same way. Whatever your x dash is goes in here after you've rearranged it. Whatever your y dash is goes in here after you've rearranged it. So we'll do question 7 just to test some understanding here. 7a specifically. Now I should probably write this one down so I don't lose track of what the actual answer is on this one. 2x squared, possibly. I'm still finishing it myself, so congratulations on getting there faster. Cancel down. Yeah, 2x squared checks out. Nice. Yeah, exactly. Brilliant. And well done getting there faster. Okay. Any further? Yeah, all this is basically the same sort of stuff now. So it's just getting a bit more complicated with how the transformations look. What are they doing on the CAS? On the CAS, okay. So the A and the K, just for fun, yeah, we'll try 9A just because now we're going to have some. It's slightly different in the sense that you don't have like a numerical answer; you have a variable answer. What would this therefore look like? We'll answer the actual A maybe later. At the very least, I'm going to start with, yeah, kx take k all squared. Yeah, that's a good place to start. As a follow-up to that now, this is where it gets less transformation and more so families of functions style things. In fact, you might have actually seen this when you guys have been doing quadratics, which I'm pretty sure most of you should have at least seen before. That is a pretty typical thing, having your kx take a all squared and knowing that it goes through a certain set of points. Figure out the values of a and k. These are always simultaneous equations. So these points are ways to substitute out our x and y variables, leaving you with two unique equations that have a and k in them. From there, you can simultaneously solve. In this case, they're saying use the CAS. This doesn't look like it would be that hard to do without the CAS, but just because it did say use CAS, I'll show you what that looks like. So I'll use the TI Nspire because it is the better calculator. And then afterwards I'll crawl my way through the Casio and see if I remember how to do it there. But okay, for simultaneous equations, my first recommendation is to start by defining your function. It's menu 1, 1 for define, or you can just click through the menus. Call your function whatever you want, just some letter, bracket x, and then plug in the unknowns into that. So you're going to have your k times bracket x take a all squared. My a is bold, which means I'll need to fix that, but we'll fix that. Menu 1. If you've already defined a variable before, then just go delete variable and whatever the variable is. That way you won't have any issues with variables that have been mapped to things that you don't want them to be mapped to. So now when I print my h of x, I should just get back what I spat out. Menu 3, 7, 1. So solve system of equations, and then again solve system of equations. From here we have two equations because we have two unknowns, and those unknowns are a and k respectively. From here it becomes pretty easy to sub in your points. So the point 1, 1 just means y equals 1, x equals 1. So y of 1 equals function with x equal 1. So by defining your function earlier on, you've made life a bit easier for yourself because you don't have to repeat the entire thing several times. So that's 1 equals h of 1, the other would be 4 equals h of 2. Just hit enter, and you're going to get two possible pairs. Makes sense to me because if you imagine trying to unwrap this, it's a quadratic. So it's likely going to have two solutions. So you have two possibilities for A, and then each of those possibilities of A have a unique possibility for K. There were no restrictions on A or K, as far as if they're positive or not, or negative. So both of these will be considered valid. When you give your answer, you say A equals 0, comma, K equals 1, or A equals 4/3, comma, K equals 9. Both of those are valid. As far as how you would do that by hand, well, let's see how complicated it gets. Just make some room for new page. One equals K bracket, it was X, yeah. So 1 minus A all squared, that is function 1, or equation 1. The other one was 2 comma 4, so 4 equals K bracket 2 minus A all squared. That's equation 2. From here, the most immediate thing to me is just divide both equations by each other, thus cancelling out the K. So doing that division, let's call it equation 2 divided by equation 1. 4 divided by 1 is 4. The K's cancel out. 2 minus A squared on 1 minus A squared. Multiply denominators. 4 bracket 1 minus A all squared equals 2 minus A all squared. Expand, expand, combine them into quadratics, solve those quadratics. Does anyone want to see me do the rest of this, or is it clear enough where you would go by hand on this? Otherwise, we can look at some other questions. Nice. Okay. Determining transformations. So in the 6 or so remaining minutes, we'll have a look at how to do that last document. I guess, by the way, before I do that, both of these are found in the classroom under the functions and relations module and the transformations subfolder within those. So if you want to see where I got all these from, I've put them there for you. And this will also be recorded in the past recordings section. That'll be up at least by tomorrow, because it takes a while for these to buffer. Okay, so these get pretty complicated. I'll do one myself, and then we'll try and do the other one. Well, I say myself, we'll do it together, and then I'll try to do the other one with just letting you guys do it. Okay, y equals x squared. So we're going from y equals x squared to the new transformed quadratic. So I'll just copy this down on the handwritten notes. We're going from y equals x squared, and we're transforming to the new function. So that's going to get y dash equals 2 bracket x dash minus 1 all squared plus 3. Okay, so now that's transferred over there, what I'll do is I'll just bring up the steps we follow on the other screen share. Step 2, get all the y factors on the y side and the x factors on the x side. So that is the next thing we're doing. What would we have to do? Nothing changes here. What does this now look like? And if you don't want to type out the whole thing, you can just say what operations you would do. Move the 3, divide by 2. Yes, precisely. Y dash minus 3, divide by 2, x dash minus 1, all squared. Perfect. Cool. So that's that stage. Next stage is to equate the x components to each other and the y components to each other. What would that look like? y equals y dash minus 3 over 2, and x equals x dash minus 1. Yes. Y equals y dash minus 3 on 2, comma, x equals x dash minus 1. Perfect. Okay. From there, rearrange for x dash y dash. Well, sub into the original function. We're not trying to apply a sequence of transformations anymore. We're trying to figure out what would have been done to go from one to the other. Because, yeah, look, full display, yes, if you put this into the original function, you will get this function here. That's not quite what this question is asking you to do, though. It's asking you to figure out what are the transformations that get you there. And yeah, that's what Carter's now mentioned. So he's done what's he done? DRT, and then x first, y second. Okay. Just hope with no fractions. Yeah, no, that's fine. I'm just trying to figure out what was done exactly. Okay, x dash y dash subject. So yeah, that'd be the first thing. Let me just keep up. So 2y equals, you'd say 2y plus 3 equals y dash, x dash equals x plus 1. And so there's your translate 1 right, that's good. Dilation 2 from x, that's good. And then 3 units up, that's good. Yeah, in that order is perfectly fine. Cool. Just for funsies, if you wanted to do TRD instead, you rewrite this as 2 bracket y plus 3 over 2. And then you do TRD. It's fine though. This is already in that form, just use that. So if you're already happy with that, then by all means, go ahead. Okay, that is more or less as complicated as those get. Now, that was untransformed to transformed. There are some nastier ones like linear tends to get weird because it's very hard to say, is this an X or a Y thing? This is where it gets even more ambiguous, what you end up doing. My approach has always been to just chuck everything over to the Y side and then just say there is no X transformation because, I mean, when you think about it normally, this is your Y-intercept. It's a Y translation. And this is a dilation directly attached to, yeah, I mean, when it's a multiplication, you can think of it as like the whole thing. There's a lot of ways you could do it, basically. I personally move everything to the Y side for linear. You could do basically anything you want there. And then there's weirder ones where they're both transformed, so rearranging for x dash y dash might be necessary. And for whatever reason, question 4 is just kind of almost completely different to what we're talking about entirely. But okay, that is time. We've made pretty good progress there, doing the entire, pretty much everything transformations related there. Like when I say that 7E is usually skipped a lot because of, well, reasons. I don't know really. Just usually is. Well, okay, that is end of class there. Does anyone have any final questions for me? Otherwise, I'll let you enjoy the rest of your day. Thanks, Ricardo. Thanks, Pierre. Have a good day.